The Doppler effect is often visualized by showing a moving particle source like this one sending waves out in all directions. It clearly shows the compression of the wave in the direction of travel and the rarefaction of the wave in the opposite of the direction of travel. However, the physics gets more interesting when we consider the movement of waves in relation to two sources, such as the application of Doppler radar to ascertain the speed of a moving object, like a person on a skateboard.
Imagine a world where a speed limit is imposed on UBC skateboarders. Pictured is Campus Security Officer Owen Smith on patrol with a standard issue RCMP Doppler radar gun.
He's too far away, I can't get a reading. Hey you! Hey you! Get back here! Do you know how fast you were going?
The SSL, or skate speed limit, is clearly labeled in many spots on UBC campus as 11 kilometers per hour. Let's calculate how the officer knew the skater was exceeding the limit.
To attempt to model this situation, we took the basic Doppler equation and decided to iron out some values that could either be canceled or determined. Now in this situation, we know that the frequency of the wave is the frequency of the microwave emitted by the Doppler radar gun, and that Vs can be canceled because the radar is not moving, therefore the velocity of the source is 0. We also know that the sign of the top half of this equation is going to be positive, as the skateboarder is moving towards the source, resulting in a compressed wave and a higher frequency. In addition, we know that the velocity of the wave is the speed of light. Now we also know that the wave being reflected off the skateboarder is what's being registered by the radar gun, such that the velocity of the source can be reintroduced into the equation, given that the skateboarder has now become the source and is moving towards the observer, making the sign negative. Now, let's define some values. We know that c is the speed of light and is equal to 3 times 10 to the 8th meters per second. But we also know that the frequency of the wave, a microwave in this case, is known to be 10.5 gigahertz according to our source. To convert gigahertz to hertz, we just multiply it by 10 to the negative 9th, which acts as a conversion factor. When putting all this together, there is something of note. Velocity of observer and velocity of the source are both now the same, given that the skateboard is acting as the observer in the first part and the source in the second.
We know that the Doppler shift is equal to the reflected frequency minus the original emitted frequency. Here, we plug in the value for the reflected frequency that we previously derived. After a little bit of algebraic manipulation, we then make the approximation that 1 minus v over c is relatively equal to 1. We can say this because we know that v is much smaller than c, v being only a few meters per second and c being the speed of light, which is 3 times 10 to the 8 meters per second. We now have an equation that will give us the original speed of this skateboard as it relates to the speed of light, the Doppler shift, and the original frequency emitted. We then plug in the data recorded by the machine during the altercation. After converting meters per second to kilometers per hour, we can clearly see that the skateboarder was in fact exceeding UBC's skate speed limit.
Let's get serious for a second.
You were clearly in violation of the speed limit.
There must have been something wrong with your Doppler calculations. I'm sure you inverted a sign somewhere. Did you consider the double Doppler shift? Did you?
Look, buddy, we just went over this. The double Doppler shift is right there, okay? Look.
It says here I'm only
0.268 over the speed limit.
0.268 kilometers an hour. Please tell Santa Ono to change something about this.
You know what? That's up to him, but for right now, you're detained.
We hope that you've enjoyed our video project and also that you learned a little bit about the rules and regulations of skateboarding at UBC and also how a Doppler radar works.